In lesson 11.2, we're going to look at partial sums of geometric series. So we're going to consider a geometric series that has 100 terms, and first term is 3, and common ratio is r. If we want to find the 100th term, a sub 100, we know that that's equal to the first term, 3, times r raised to the 99th power. We're going to use that to write an expression for the 100th partial sum. Remember, that's the sum of the first 100 terms. So s sub 100 is equal to the first term 3 plus the second term 3 times r plus the third term 3 times r squared. And we're going to stop there writing the terms explicitly and continue with a plus and then an ellipsis. And then we're going to write the last term, 3r to the 99th, explicitly. Now next, right below this, we're going to write an expression for r times the sum of the first 100 terms. And if we multiply all the terms in the first equation by r, what we get is a first term 3 times r, second term 3 times r squared, and our last term is going to be 3r to the 100th, but the term immediately before it is 3r to the 99th. Now what we're going to do with these two equations is we're going to subtract everything in the second equation from the first one. So s sub 100 minus r times s sub 100 is equal to, and on the right side we have 3 minus 0, and then 3r minus 3r. These pair of terms, when we subtract those, we get 0. When we subtract these, we get 0. When we subtract these, we get 0. And the only term that's left is minus 3r to the 100th power. From here, we're going to solve for s sub 100 by factoring. So we're going to factor out an s sub 100 from both sides, from the left side of the equation, and that'll leave us with 1 minus r. And on the right side, we can factor out that 3, and that'll leave us with 1 minus r to the 100th power. In order to solve for s sub 100, we just need to divide both sides by 1 minus r. And this suggests a sum formula for the nth partial sum of a geometric sequence. Remember that 3 was the first term, so s sub n is equal to the first term times 1 minus r raised to the n power divided by 1 minus r, where a sub 1 is the first term, r is the common ratio, and n is the number of terms. So if we want to use this to find the 10th partial sum, if we're given the first term and the common ratio, then I'm going to use this formula, s sub n is equal to a sub 1 times 1 minus r raised to the n power divided by 1 minus r, and just replace the values. So a sub 1 is 128, and the common ratio is negative 1/2. It's really important that you put that common ratio in parentheses, particularly when it's negative and when it's a fraction, and that exponent needs to go outside of it. That'll be important when you're doing your calculator entry. And then downstairs, 1 minus the common ratio of negative 1/2. I want you to notice something. Notice that when we found the 10th partial sum, the n got replaced with 10, and the n got replaced with 10 over here on the right side of the formula as well. So from here, we can just enter this expression into the calculator. Control divide for a fraction. 128, open parentheses, 1 minus, and then open a parentheses for the common ratio. Insert negative 1/2 inside, cursor outside the parentheses, and use your exponent key to raise it to the 10th power, and then divided by 1 minus negative 1/2. And that'll give us 341/4. which is fine to write in exact form, but we can also get a decimal form, and sometimes for geometric series, this will be easier to write it in decimal form, 85.25. All right, your turn to try the next one on your own. Pause the video while you do this. Here's the answer to this one. When you're doing these sort of computation, make sure that you're writing down the computation that you're entering into your calculator, and that will be your form of showing work. And then if you choose to give a 3 decimal place approximation, make sure you're rounding to the nearest thousandth. In example 2, we do have the first term given to us, which we need for the sum formula, but we don't have the common ratio. But since we have the 6th term, we can relate the 6th term and the first term. The 6th term is equal to the first term times r raised to the 5th power. So our 6th term is 18, and our first term is 2/27. And now in order to solve for r, we need to multiply by 27 over 2. So 18 times 27 over 2 gives us 243. So 243 is equal to r to the 5th. And now we need to take a 5th root. And the easiest way to take a 5th root on your calculator is to raise 243 to the 1/5 power. So 243 raised to the 1/5 power gives you 3. All right, now we know the ratio and we know the first term, so our sum of 9 terms is equal to that first term, 2/27, times 1 minus the ratio, which is 3 raised to the 9th power over 1 minus 3. Entering that on your calculator, we're going to get 19,682/27, and we may want an approximate value. So press Control and Enter to find that value, 728.963. All right, your turn to try the next one on your own. Pause the video. Here's the solution. In the next example, we're asked to write in sigma notation and then find the sum using the sum formula. So what we know here is that this is a geometric sequence, and to get from one term to the next, we're going to multiply by 1/2. So our first term is a sub 1 equals 3, and our common ratio is 1/2. We can use that to find a general expression for the nth term, and the nth term in a geometric sequence is the first term times r raised to the n minus 1. So that would be 3 times 1/2 raised to the n minus 1. We know that our sequence starts with the first term, but we don't know what number term that last one is, so I'm going to set 3 over 2048 equal to 3 times 1/2 raised to the n minus 1, so that we can find the value of n for that term. Let's divide both sides by 3. That'll give us 1 over 2048 is equal to 1/2 raised to the n minus 1. If we solve for the exponent n minus 1, that's equal to a log base 1/2 of 1 over 2048, or n is equal to 1 plus the log base 1/2 of 1 over 2048. We can enter that in on the calculator, and that'll give us an n value of 12. Remember that that means that this is the 12th term of that sequence. So when we're writing it in sigma notation, this is the sum as n goes from 1 to 12 of 3 times 1/2 raised to the n minus 1 power. That's one of our answers, writing it in sigma notation. Then we're going to use our partial sum formula to find the sum of those 12 terms. So the sum of the 12 terms is equal to the first term times 1 minus the common ratio raised to the 12th power divided by 1 minus the common ratio. That gives us 12,285 over 2040, which we can approximate if needed. And that gives us a value of 5.999. All right, your turn to pause the video while you try the next one on your own. All right, here's the solution for that one. Now let's move on to a different type of example. In this sequence, we have the general term here, And that general term can help us find the first term, and it can also help us find the ratio. So a sub n is equal to 5 times 1/3 raised to the n plus 1. And that means that if I want to find the first term, I replace n with 1. And so now we have 1/3 to the, that'll be the 1 plus 1 power, which would be the second power. 1/3 to the second power is 1/9, times 5 is 5/9. Our second term is 5 times 1/3 raised to the 2 plus 1, which would be 5/27. So clearly our ratio here is 1/3. And so I can find the sum of the first 20 terms by finding the first term, which is 5/9 times 1 minus the common ratio of 1/3 raised to the 20th power divided by 1 minus the common ratio of 1/3. Entering that computation, we get a 3 decimal place approximation of 0.833. In example 5, we're going to compare our answer to that previous example, example 4, to that the computation that's given below. And then we're going to look at why they're approximately equal. So the computation below is 5/9 divided by 1 minus 1/3. In exact form, that gives us a fraction 5/6. But if we find the decimal approximation, it's also 0.833. Now let's take a look at why these two are approximately equal. If we take a look at the computation in the calculator, I'm going to scroll back up to that. You'll notice what's in parentheses here, 1 minus 1/3 raised to the 20th power. I'm going to take 1/3 and I'm going to raise it to the 20th power, and we're going to see what that result is. So 1/3 raised to the 20th power is, we get a very small fraction. Let's get a decimal approximation of that. When you do that, you're going to see this in scientific notation, about 2.9 times 10 to the negative 10th. That's a very, very small number, which is very close to 0. So, since 1/3 raised to the 20th power is very close to 0, then 5/9 times 1 minus 1/3 raised to the 20th power over 1 minus 1/3 will be close to 5/9 times 1 minus 0 over 1 minus 1/3. In other words, that 1/3 to the 20th power is really close to 0, so we can just approximate it as 0. And then we just have 5/9 times 1 over 1 minus 1/3, which is the second computation that we did. What this tells us is that when I have an infinite number of terms, the sum is going to move toward 0.833. In example 6, we're determining the number of terms in a geometric series where we're given 2 terms. We're given the fact that we have a positive ratio and the nth partial sum. So what we know about a sub 3 is that it can be computed by finding a sub 1 and multiplying by r squared. A sub 3 is 162, a sub 1 is 200. We can use this information to solve for r squared, first dividing by 200, and then let's reduce that fraction. That's 81 over 100 is equal to r squared. Since we know r is positive, we can take the positive square root of it, which is 9/10, and for our purposes for writing that, it might be easier to just write it as 0.9. So let's take a look at our sum formula. Our sum formula is s sub n is equal to a sub 1 times 1 minus r raised to the n power divided by 1 minus r. We know s sub n, which is 1856.42, but we don't know n, the number of terms. We also know a sub 1 is 200, and we know that r is 0.9. So, simplifying, 1856.42 is equal to 200 times 1 minus 0.9 raised to the n power over, and in the bottom of this fraction we have 1 minus 0.9, which is 0.1. We can now multiply both sides by 0.1, which will give us 185.642 is equal to 200 times 1 minus 0.9 raised to the n power. Dividing by 200, we get 0.92821. Next we can subtract 1 and then divide by negative 1. Which will allow us to find the value of n using a logarithm. So n is equal to the log base 0.9 of 0.7179. Oops, that's not, I'm off by a digit there. That's log base 0.9 of 0.07179. So log base 0.9 of, and that will be the opposite of that answer that we have previously on the calculator, so I don't have to retype it. And that gives us 24.999. Remember, this was an approximate sum, so we have an approximate solution of 25, which is the number of terms in the series. We have a couple of word problems to apply here. A woman made $30,000 during the first year of a business that she started, and she made an additional 10% over each previous year for each subsequent year. We're looking for how much money she made during the fourth year of business and then her total earnings for the 4 years. So let's make a table of values, the year and her earnings in dollars. So in year 1, we know that she made $30,000. When we increase a number by 10% for her second year of earnings, we take that 30,000 and we multiply it by 1.1 for 110%. In the third year, we'll multiply by 1.1 again, and then in the fourth year by 1.1 again. There's our fourth year of earnings, which is really the fourth term of a geometric series. So 30,000 times 1.1 raised to the third power is going to give us our fourth year of earnings, which is 39,930. And then we want to know her total earnings. That means we're going to add all of these together, or we're going to find the sum of a series. So we're going to use our sum formula. The sum of 4 terms is equal to the first term, 30,000, times 1 minus the ratio, which is 1.1, raised to the fourth power over 1 minus the ratio. Let's enter that in. 30,000 times 1 minus 1.1 raised to the fourth power over 1 minus 1.1, and that's 139,230. In our last example, a college student jokingly asked his parents to charge him for room and board according to the geometric sequence, 1 cent on the first day, 2 cents on the second day, and 4 cents on the third day, and so on. This forms a sequence where our first term is that 1 cent, and the common ratio is 2. We want to find the total room and board, so we're going to add together all those rents. So we're going to find the sum of 30 daily rents. And that sum would be the first term times 1 minus the common ratio, which is 2, raised to the 30th power, divided by 1 minus the common ratio. Let's enter that and see what the total rent would be. So that's going to be 0.01 times 1 minus 2 raised to the 30th power divided by 1 minus 2, and that gives us 10,737,500 $418.23. So even though it may sound cheap rent for the first several days, this gets expensive really fast.